All right, I think the time is slowly approaching. We are at 16:45 Lviv time, or wherever you are in terms of time zones. I guess I'm very, very happy and very pleased that I can introduce our next speaker, who is Benjamin Maier from the, I think, still officially affiliated with the Humboldt University, if I understand correctly, but moving soon to Copenhagen, to the Center for Complex Social Systems, if I...
Yes, that's correct. Social data science.
Complex social data science, but still working on complex systems, on human complex systems, but then in a different location in Copenhagen. So Benjamin studied physics at the Humboldt University and did also his PhD officially at the Humboldt University. However, here he was working with Dirk Brockmann, and Dirk Brockmann is not only a physicist by training, but also he's affiliated with the Department of Biology. But even more importantly, he's a head of the epidemic modeling group at the Robert Koch Institute, which is the national epidemic research institute in Germany. So Benjamin did his PhD on modeling of epidemic diseases and analysis of data on epidemic diseases, and which kind of make him perfectly suited for what was keeping us so busy over the past 2 years or past 3 years, namely the COVID pandemic. And Benjamin was actually, together with Dirk Brockmann, published some influential papers, for example, studying or explaining the observed sub-exponential growth in the early pandemic, COVID pandemic in China, and as well as other papers analyzing, for example, the mobility patterns in Germany. So I'm very much look forward to Benjamin's talk to learn more about how complex systems research and maybe a physics perspective can help us to understand also epidemic spreading and current and pandemic and what happened over the past 2 years. I should note that Benjamin is actually joining us from his holiday, so very thankful for that, but for him it's very early in the morning, so he's joining us from the US. So I hope nevertheless this works for you, Benjamin, and with this I would hand over to you and to your talk.
All right, thank you very much, Pavel. I will quickly try to share my screen. In the test session, I was advised to share my screen entirely. So can you see the full screen?
Yes, we can.
Awesome. That's great. So first of all, I would like to take the opportunity to thank you, Pavel, and Yuri, and everyone who has been organizing this workshop for inviting me here. I feel very honored to be part of this. And I feel devastated to not be able to visit you personally in Lviv, but given the circumstances, I very much hope, fingers crossed, and I pray that I can be visiting you at some later point next year, years later. So yeah, all my best, all my thoughts and all that go to you. And I'm very impressed that you're actually going through with this workshop. Nevertheless, I'm gonna give a lecture here about fighting the pandemic with complexity science. This is the first time that I'm giving a lecture like this, so it might happen that I get stuck somewhere or that some things are not quite polished. I apologize in advance, but I hope that this works out in the grand scheme of things. Nevertheless. All right. So first of all, I wanted to introduce myself too. Pavel already did a great job, but I thought I introduce myself a bit too. I'm Ben. I owe this patch of hair loss to my bachelor's, which I did on theoretical work on the strong nuclear force in confinement. And these bags under my eyes I owe to my master's degree, which I did on theoretical work on single atom thermophoresis in liquids. So I studied physics, as Pavel said, at Humboldt University, and I switched between fields a lot. And And finally, I did my PhD in 2019. This picture is from 2019, where, as you can see, I was still smiling, even though I was currently finishing my PhD, which I did in epidemic spreading on face-to-face contact networks. This was 3 years ago. So now I look like this. This is a selfie from last night. I now have a patch of gray hair and my smile is gone because I have been working as a postdoc at the Robert Koch Institute, which is Germany's central center for disease control during a pandemic. So it has been quite a stressful time. I am working at a team led by Professor Dirk Brockmann, as Pavel said. Dirk calls the group Research on Complex Systems, short ROCS. We are a lovely group. I mean, not talking about me, but everybody else. Lovely people. I love them all, 15 of them. And none of the work would be possible without any of them. And also not without Mowgli, who's our Senior Parks and Recreation Officer, Office Dog. Right. So the research we do is usually centered around how structure influences structure of contacts, or how humans interact, or how systems interact influences spreading dynamics. Called Research on Complex Systems, but in the last 2 years mainly involved with infectious disease modeling and data analysis regarding infectious diseases. Our job in this regard, usually when there's an infectious disease outbreak, is to give answers to very simple questions, which are: where is the disease going to be at which time? How many people will be affected? And what can we do to mitigate its spread? The questions are simple, but seemingly the answers are complex. So what has been happening in the last 2 years is that various groups, ourselves included, published incredibly complex models to describe the spread of COVID-19 and how the public and government legislative reacts to it. This is just an example. Usually what's done is that the population is split into several compartments. I'm relatively sure you will have seen stuff like this. Then you have millions of parameters trying to accommodate the time delays between how individuals change states and the probability of stuff happening. And then medical professionals are always very keen on having very many different age groups that interact in certain ways. So this is from colleagues of us, Scholz et al., very complicated. This is a complex model by Steinegger and Alex Arenas. So each of these states you have to think of as in a single patch, but then ×3 for age groups and times, I don't know, 100, I think, or 100 municipalities, and then these municipalities are connected so people can commute between them within the model, and it all gets very involved and complicated very quickly. This is a model by colleagues Prieselmann et al., who considered vaccinations and also the self-regulated behavior in response to a growing crisis, also with age groups and contact communities. And here's a model that we ourselves came up with to analyze the impact of contact tracing. Right, so my point here is that all these models are relatively complex, and this is just one simple flavor of modeling, which is the analysis of ordinary differential equations, usually coupled ones that have that are of second order to accommodate for infections. There are also other things like integrative models or agent-based models, and they can get very involved. What I learned from physics however, is that in physics, what you do when you look at a system is that you distill the essential of the systems regarding the question that you ask about the system. So for example, if you look at the system, there's a human and there's a fairly simple machinery that lifts a log with a pulley. And from first year of mechanics, we all know that we can get rid of all this stuff and look at this. So we have a pulley, and then there's some force in the rope and a mass and a gravitational force. And also we know that we can essentially get rid of the pulley too. So we just can look at this. So I'm always very inclined, or I grew more concerned about this principle in modeling too, is that all these involved models kind of make it hard to convey the message of what's going on and to see the essential and to learn about the system in an intuitive way. There's a design principle from design that's called KISS. It stands for Keep It Simple, Silly. I think it comes from the American Navy, actually, which means that if there's a possibility to solve a problem in a very simple way rather than complicated way, go for the simple way. And I would like to keep this lecture a bit centered around this principle today. So today it's the Keep It Simple, Silly modeling extension version of that. Right. Before I go, so I'm going to go a bit more in the basics, and I hope that I'm not boring anyone with it. I try to give a bit of a different perspective on what's usually taught. I hope that that's that that's not like super known already. But instead of going for the infectious process, I first of all wanted to start with a very, very simple, just reproductive process that comes from theoretical biology. So let's just think of a species called A, and within the species, every individual produces new individuals until it eventually dies or is removed from a reproduction process. So we can write that down as chemical equations. So A decays into 2A particles, and eventually A with the rate rho decays into the void. And how can we think of this in a more mechanistic way? Well, let's look at a timeline and say that when an individual is born, it will eventually die after a lifetime tau. However, this lifetime tau doesn't have to be fixed. It usually can be shorter or longer, so it will follow a probability distribution P. Within this time frame, its lifetime, it will give off new offspring. So there's an offspring event here or there or there. In principle, there can be M offspring events within this time frame tau. So we would say that the number of offspring given the lifetime tau is distributed with a distribution omega that depends on tau. And together with the probability distribution of the lifetime, we can write down the distribution for the number of offspring, which is just the product of both these probability distributions. Right. So, of course, these probability distributions can have complex shapes, but here I will just settle for the easiest way, which is that we look at Poisson processes, which means that these processes in an infinitesimal amount of time happen with a certain fixed probability, and certain others I'm simplifying here, which just means that the lifetime will be distributed with an exponential distribution with mean 1 over rho. Rho is the removal rate. And the number of events will be distributed according to a Poisson distribution with mean eta, which is the reproduction rate, times the lifetime. Right? So when we ask what is the average offspring per individual, we can just take the average. So first of all, we write down the average over the number of offspring given the lifetime and integrate over all lifetimes. So first, let's do the average over omega with a Poisson distribution. This is just the mean, which is eta times tau. And then you recognize that the tau here, this gives the formula for the average of the lifetime. So we can just put that in. The average lifetime is 1 over rho. So we obtain that the average number of offspring is eta over rho. We call that the basic reproduction number because it is the average number of offspring per individual, the average reproduction. Okay, so we can also rewrite this process in another way, or think of this process in another way, not a stochastic way, but an average way. And if the number of individuals in a species is fairly large, then the average way will coincide with the mean of the stochastic way. Here we think of gaining rates. So K plus is when the number of individuals is A, then the rate with which new individuals are born is eta times A, and the rate with which individuals decay is just the removal rate times A. So we can write down the temporal change of A as the difference between those two rates. That's just given like this. And of course, this is the most simple of all ODEs, and the solution is as this. So we see that there's either exponential growth or decay or constant at the critical point, the number, the population size is constant. We can also rewrite this and pull rho out of this bracket, and then see that there's that we can rewrite this as exponential function of something here in this bracket, eta over rho minus 1, and we recognize this as the basic reproduction number. So we see that in this simple, very, very simple, the most simple of all cases, the increase or the growth of the number of individuals of A is given by the basic reproduction number minus 1. Essentially, this means that if the average offspring per individual is larger than 1, then there's a positive growth rate, so exponential growth, and if the average offspring per individual is smaller than 1, then there's a negative growth rate, so exponential decay, which means that at R0 egg equal to 1, we are at a critical point and a phase transition. All right. So instead of looking at a single species, we can also look at several species. So for example, if a single individual of a species AI does not only reproduce itself necessarily, but can also, during a reproduction event, cause another individual of another species to be born. Think of it as spontaneous mutation, for example, with some rate eta ji. And of course, we will still carry death. So each species can have its own removal rate. What we can do then is to write down the mean evolution of the number of individuals with the operators eta and rho. So these are matrices. And then solve this with a matrix exponential, which looks like this. Right? It's very straightforward from the one-dimensional case. Then we can take this operator rho and take it out of the bracket and see that we get a matrix exponential, which looks like this. We have eta times rho to the minus 1 minus identity matrix, and then the matrix exponential of that. And we identify from this two operators, namely the growth matrix, which is just the Jacobian, the difference between these two growth rate matrices. And the second one is the so-called next generation matrix. It is called that because it describes the generational growth of a population that is encaptured in the vector y. So think of it as if you have generation g and a distribution between species, and you apply the operator k, then you will get the next generation yg plus 1. So this generational growth equation, of course, means that over a few generations, after a few generations, this will approach an eigenstate, an Eigenzustand, which is dominated by the eigenstate that corresponds to the largest positive value of k. And actually, the basic reproduction number is the spectral radius of this operator. And in the other case, or in this other picture, where we just look at growth matrices, the state A will approach the eigenvector that belongs to the largest eigenvalue of this operator lambda. So this is just a sketch of a very involved proof that whenever the basic reproduction number is larger than 1, there will be a positive growth of cases, or positive growth in this case of individuals or species. If the basic reproduction number is smaller than 1, then there will be an exponential decay. So now you might have been asking yourself that you were promised a talk about diseases, and nothing about this was about diseases. So let me replace the equations for reproduction with equations for infection. Here, this is a slightly more complicated process. So an infected, so what we're looking at is not the species A anymore, but infected, called I. And we also have susceptibles, S. And this equation simply means that there's a reactant necessary for the reaction to happen, right? And the reactant is a susceptible individual, which is, upon contact and infection event, converted into an I individual. But that just means that we can apply the same math to it. But instead of just having a linear equation, we do have a nonlinear equation here, in the sense that S is the probability that a contact of an I individual is susceptible, and this probability changes over time the more and more infected, so I individuals, are produced. And now eta is not the reproductive rate anymore, but the so-called contact infectivity. So it's a rate with which contacts become infected. However, it has the same structure as the equation before. And we can say that if we just look at a single point in state, in the state space, where we set S as constant for around this. So let's say the process is around a point in the space, it's constant. And then we can compute the reproduction number, which is the same as before, but we have this S here, the probability that a contact is susceptible. So this is what we call in infectious disease modeling the effective reproduction number. And if we assume that initially the probability that a contact is susceptible is equal to 1, then this just reduces to the reproduction, so the basic reproduction number. All right, so I've been showing you very complex infectious disease models in the beginning. So let me just tell you that in general, we can write down very involved models that can have as many states as you wish, with as many rates as you wish. But in principle, it's always quadratic terms that describe infections and linear terms that describe transitions between states. And in general, the recipe for dealing with this is to identify all susceptible and infectious states, and then compute a transmission Jacobian around the current state of susceptibles. So this would correspond to this term, and then the transition Jacobian from this term, that just from this term, and then around a state of susceptibles, rewrite the system as linear with this transmission operator that depends on the state of susceptibles and the transition operator. And then we, as before, can rewrite this as such with the next generation matrix or next generation operator. And the reason I'm telling you this is because the things or the models that I've been showing you before usually are written down as ODEs, and then these ODEs are integrated and numerically, and then the numerical solution is analyzed with lots of figures. And in my opinion, oftentimes the analysis of the spectrum of this operator is just simpler than integrating an ODE system. And often it's not necessary to really integrate the ODE system for the questions that you ask. All right, instead of this operator, I will briefly look at the linear case again. So the effective reproduction number. Our mission as researchers at a public health institute is containment, right? So we are pledging to legislators, to the public, to institutions, and do analysis and hope that our efforts will push the effective reproduction number below 1, such that the exponential growth of infecteds will turn into decay instead. All right, so I want to look at this very simplified equation of the basic reproduction number, or representation, the one-dimensional, which is, we have here the basic infectivity, eta. We have the probability, or the number of infected, susceptible individuals, and we have the removal rate. And in order to get the effective reproduction number as small as possible, we can tackle each of these with different measures, right? So we could reduce the infectivity, which is done with, for example, if it's a respiratory disease like COVID-19 with masks. We can reduce contacts, because implicitly contacts are here in this rate as well. And we can vaccinate people. This is not super obvious immediately, but vaccinations, as you probably already know from COVID-19, are not perfect, which means there can be breakthrough infections, but also it has been observed that breakthrough infections are not as infectious as unvaccinated infections. So that is something we can handle with vaccinations. We could also reduce the number of susceptibles in the system, or the probability that a susceptible is encountered. We can do that with drastic NPIs, non-pharmaceutical interventions like lockdowns, or also vaccinations, because vaccinations, while not perfect, will reduce the probability of a vaccinated person to become infected. Or we could increase the removal rate, which is done by isolation or quarantine, or with increased testing. Our most effective tool in a box is actually isolation in quarantine. It's also the oldest, or one of the oldest measures that can be taken. And I just want to give a brief intuition about what it means in an applied sense. So what I've been showing you is just a very simple model for infection so far. So from a public health point of view, what people usually, or epidemiologists usually think about is a chain of events that is as follows. You have an infection that takes place. Then after a certain incubation period, there will be a symptom onset, so the person becomes visibly sick. And there is an infectious period while the person is sick, and during this infectious period, they can infect other people, and then until they recover or die in the courses of events. Until that, they would be able to infect other people. For Ebola, the infectivity of a person is relatively high only after symptom onset. So you have a high chance of seeing that if someone shows symptoms of Ebola and you isolate them on observation, that you can reduce the infectious period relatively quickly just through isolation, which means that we increase the removal rate drastically, which decrease the reproduction number, and such the system can relatively quickly become subcritical. The same worked for the first SARS epidemic, where the infectivity or the viral load in the throat was peaking usually on the day of symptom onset or a day after, actually. So this is very effective. You see or you diagnose a person with the symptoms, you isolate them, you drastically increase the removal rate such that the reproduction number decreases. Well, for COVID-19, the story is a bit different. It was very quickly found out that the incubation period is not equal to the latent period. Latent period is the time between infection and becoming infectious. So for COVID-19, as you probably already know, it means that the infectious period begins before symptom onset. And also, we do have asymptomatic infections where there's no symptom onset at all. So you cannot just base removal or the increase of removal rate on diagnosis and the observation of symptoms. This is relatively problematic for us because we do not have much leeway in reducing the removal rate, which usually is the least invasive of interventions. We do have to rely on these other interventions, which is we have to reduce the infectivity or shield or take enough susceptibles out of the process by lockdowns or vaccinations for the effective reproduction number to be sufficiently small. I will now transition from this relatively general part of the talk to more of work that we did in our group, and I will concentrate first on vaccinations. So, in October 2021, what happened in Germany is that despite having a large number of vaccinations in the country, which was around 2/3 of the country being reported as vaccinated, the number of cases rose dramatically, exponentially actually in October, and ICU admissions quickly followed as well. And it was reported that 40% of the new cases were breakthrough infections, which sounds a lot. So the question was what to do and how to assess the situation. Of course, government could have said sent society into a general lockdown again. But the negative side effects of these drastic interventions always have to be weighed against the positive effects. And also it probably would have been judicially close to impossible, because from a court point of view, being vaccinated is having done your part, and a lockdown takes away your freedom. And from a court point of view, it's not justifiable to take away your freedom if you've done your part as being vaccinated. Other interventions were the booster vaccination, which was around the corner at the time, or, for example, targeted contact reductions. So what we needed at the time was a method to basically assess the contributions that the vaccinated and unvaccinated individuals made towards the infection dynamics, to see which intervention would work and whether or not vaccinated people actually contributed a lot to the dynamics. We wrote a preprint that you can find under this address. I want to go back to this slide for a moment, which I told you is the general form of how infectious disease models could be written down in the form of ODEs. And what we decided back then is to ignore the ODE part and just go for the analysis of the spectrum of the next generation operator. Right, so what we did was to identify the susceptible states and split them into unvaccinated and vaccinated states. And we took into account the empirical results that were available about a susceptibility reduction after vaccination and the transmissibility reduction after breakthrough infection, which all go into the infectivity operator. And then we can write down a relatively involved formula for this next generation operator that takes into account age groups down here and vaccination status up here. So this would usually be a huge ODE system, and we could integrate it and see what happens and how many vaccinated people would be infected and so forth. Instead, what we chose was to consider the generational growth, right? So take this as the number of or the distribution of infecteds of different statuses, like age and vaccination status, and the next generation operator that operates on this distribution to give the next generation. And as you see from this, it's a very simple equation, the system will quickly approach the eigenvector that corresponds to the largest eigenvalue, R0. So if we have an entry Kij that quantifies the average number of I offspring caused by a J individuum, and we have the relative share of J individuals in a total generation from the eigenvector of this matrix K, then the matrix Cij quantifies Kij times Yj quantifies the contribution to the dynamics or contribution to the reproduction of I individuals made by J individuals. I've shown you this involved operator, this one, but if you actually ignore age structure, you can solve this analytically. And we found out that the analytical solution is very much not too far off from the more involved age structural solution. And it looks like this. So we can quantify the contribution of different infection pathways with this contribution matrix. And with empirical results regarding the efficacy of vaccines against infection and transmission of Delta variant, we found that the even though 68% of the population were vaccinated at the time, the most important contribution was made, or the most important contribution of the dynamics was made from unvaccinated individuals that infected other unvaccinated individuals. And the second largest contribution was from unvaccinated individuals that infected vaccinated individuals. In total amounting for 2/3 of the infection. 2/3 of the infections at this period of the time. So the result here would be that even though 2/3 of the population were vaccinated, 2/3 of infections or 2/3 of the crisis were caused by the unvaccinated population. We also analyzed a few more things here that I will not show, which is that we looked at the contributions if both of these populations would be separated with decreased mixing between vaccinated and unvaccinated. This would amount, for example, to restricting access to public venues for unvaccinated individuals, which happened in Germany. Then the contribution would even increase for the unvaccinated. But in total, the reproduction number would go down. And of course, what we also found is that if you vaccinate more people, then the reproduction number would also go down, but that's kind of obvious. All right, afterwards, in November 21, the situation changed a bit. What's the time? I still have 15 minutes left, I think, right? Yeah. So in November 2021, there was widely in the news the spread of a new variant quickly called Omicron by the WHO. And it spread rapidly, much faster than any variant observed before, which means that the growth rate in the exponential here was quite large compared to before. And the question was why? So if we look at the derivation that we did earlier, we saw that the growth rate is something like the infectivity times the probability of any individual being susceptible minus the removal rate. And we saw that this lambda increased. So why? It could be because this variant has intrinsically an increased infectivity. Could also be because there is suddenly an increased number of susceptibles, which would mean that in a system where many people are vaccinated, that this variant would show a certain amount of immune escape. And then also it could mean that there is a decreased removal rate, which means that there's a shorter infectious period. In total, if we look at the effective reproduction number again, then the latter would be good news because a decreased removal rate increases the growth rate, but decreases the effective reproduction number, which means that even though cases rise quickly, it will not reach high peaks. We could also have okay news, which means that the increased number of that we would have an increased number of susceptibles due to immune escape. And I call this okay news because this is something one could potentially fix with booster vaccinations. And then we would also have bad news if there's increased infectivity, because then there's not much we could do, we could have done besides decreasing or like going into full lockdown. Right, so our objective at the time was a fast assessment of the possible impact that this variant could have on the population in Germany. And we focused on the impact that this would have on ICU admissions, so intensive care unit admissions. And our goal was to keep the ICU admissions below capacity. The problem is that, of course, we not particularly not necessarily in a group, but also like generally on the institute, there existed some models that were super involved. Not this one, but something like this one. I'm just using this as an illustration. And while these involved models can be useful for for researching very detailed questions, their calibration take a long time or a lot of computational power, and many of the parameters, all these rates and probabilities, might be simply unknown for the variant that is spreading at the time. So what we did was to simplify. We reduced, and got rid of age structure. We got rid of all the different compartments in between, and just went back to the basics, devised a simple SEIR model. The reason is that you can write down a simple ODE for this. So here is the decrease of susceptible individuals with an effective infectivity rate or removal rate for susceptibilities. There are several ingredients to the recipe, which is that in total, the infectivity is modulated by the mean contact or hygienic behavior. For example, if there's no lockdown, then F would be 1, and if nobody would see anyone, then F would be 0. We also put as an ingredient to the recipe the mean susceptibility reduction against a variant that comes from vaccines. So this is a population mean. And we included the base transmissibility of a variant. So this would include the biological properties of the pathogen, in this case, the Omicron variant. We looked at both Delta and Omicron as models. So in the beginning, Delta and then Omicron. We also included latency and removal rate for the variants. And we did that, or we included the E compartment because we measured growth rates, which I will come to in a minute. And for that, the latent compartment is actually important. Okay, so what one usually does is to look at the incidence, which is new cases per day or per unit of time. This is data from Germany in this period of time, so pre-Omicron. And the task is usually to find a contact modulation in your model such that your model fits the available data. And that's done usually numerically with fitting methods. For example, Bayesian methods with the likelihood minimization, or just a least square fit. But since we cut all the extra fat from the model, we were able to do that analytically here by computing the growth rate and the depletion of susceptibles from the incidence, and then deriving the growth rate from the model analytically, which is possible. And then we could just simply solve this equation for F and put in the growth rate and depletion of susceptibles from data, and then simply got our function analytically instead of having to minimize some distance functions. Here is a fit of our model. So the turquoise is data, and the dotted line is our model for the Delta variant. So just to have a quick illustration that this method actually works. Then what we did was to look at the fixation dynamics of Omicron versus Delta. And from theory, we know that this should roughly be a sigmoidal function with a fixation rate that is proportional to the difference of the growth rate of Omicron cases and Delta cases. I'm just showing you this to say that these constraints from Did someone turn on their microphone? Sorry. That these growth rates, so this data actually puts constraints on a certain number of parameter ranges, which means that effectively from this analysis and other empirical results that were collected by medical professionals, we were able to rule out that we have a super high increased infectivity. So the complete bad news could be ruled out by us. However, we wanted to, so what I've shown so far is to just like fit the model to the incidence data. What we actually wanted to look at is the number of ICU admissions, right? And usually what you do here, or what modelers do, is to have these involved networks of how individuals change their states based on race and probabilities. But I am not a big fan of that actually, because every time you change something here, you have to change something here too, so that the change would be adjusted. And so, or how I think about these models is that you send in a signal and then you have some black box or some function that convolutes your signal, and then you get an out signal. So if you just have new cases and ICU admissions, for example, you could have a signal of new cases and then multiply that with a probability that new infections will go to the ICU, and convolutes that signal with a delay distribution that you can actually have empirically or just assume, and then you get an out signal for the ICUs. So that you, and then by that, you do not have to adjust your whole model and make sure that the number of individuals is constant over time. You just have two separate things. You have your model that deals with infections, and then you have a signal, a signal convolution function that takes the signal from the model and converts it into another signal. All right. So with this model, we then very different assumptions regarding the efficacy of booster vaccinations and different mitigation strategies, and also assumed several relative risk reductions in ICU admission. So we basically took the probability to land on an ICU after an infection with Delta and estimated how large the wave of Omicron infections might become in the next few months, and then calculated how reduced the relative risk for ICU admission with Omicron versus ICU admission with Delta has to be for ICU capacity to stay below capacity. ICU occupancy to stay below capacity. Below capacity means below the size of the Delta wave in 2021. So we simulated lots of different scenarios, and the worst case scenarios that we actually were able to quickly rule out, but are shown here, were 800,000 new cases per day. But we thought that from all the different scenarios and the likelihood of different scenarios, what is more realistically was on the order of 200,000 to 400,000 cases per day. And of course, this would have been terrible news if Omicron would have been as bad on the respiratory system, as hard on the respiratory system as Delta. But it was quickly reported from the US and the UK and also Denmark that this is not the case. And we saw that in each of our simulations, if the relative reduction in ICU admission probability is minus 90% to minus 80%, then we would probably stay in the clear, even though there would be a high wave in Omicron cases. The thing was that some people asked for lockdown or hard mitigation measures early on. And from our analysis, we were able to show that this actually probably would have made things worse, because what happened at the same time in around changed from 21 to 22 is that Germany had its largest peak in the booster vaccination campaign. So if we would have had a strict lockdown for, let's say, 2 months, then the increased protection that half of the population in Germany got from the booster vaccination would have waned already by that time. And then the full force of the Omicron infection would have gone through again. Yeah, so what we showed was that longer and minor contact reductions would probably have helped, but this didn't seem to be politically possible. But in any case, we showed that the ICU occupancy would probably be below capacity. And this turned out to be the case, actually. And also the number of new cases per day was on the order of predictions, with the second peak coming by a second variant that we didn't include in our analysis, because at the time it wasn't that prevalent yet. We actually stopped our analysis, so we did the analysis until January 1 and then stopped. So what you see here is kind of a prediction for after January 1st. All right, how am I doing on time? I think I'm through. I will just quickly go through this. Or will I?
I think you have a couple of minutes, maybe 5 minutes.
Okay. So as a final thing, this is the last thing I did at the Institute 2 months ago, is to think or to have the question posed that after so many people have been infected with Omicron, especially unvaccinated people, what actually is the size of this probability, or the order of this probability, as like how many completely immunologically naive people are there still in Germany? Of course, even if we know the number, it doesn't say that much, because usually it depends on the variant that will spread later, how the effective reproduction number evolves. But it's better to have a cause estimation than nothing. So we wanted to ask this question, and we think about it this way, is that we have the population, and through over 2 years, there are many people that haven't been vaccinated, and so that haven't been vaccinated at the time they were infected, but these people could have been vaccinated later. So we have a vaccinated population, and we have people who weren't vaccinated when they got their infection, but we do not know the overlap of these two populations. However, we do want to know the size of this black area. All right, we do want to know who's left, or how many people are left. Problem is that we do not know exactly the size of this circle, and we don't know the size of this overlap. The size of this circle, however, we can estimate by looking at zero prevalence studies. And what people do there is they take blood samples and look at the antigen concentration of blood donors, actually, and compare that to the number of reported cases. So we could get an ascertainment factor between reported cases and actual cases. And then second, for this overlap, we can make an ansatz that the virus doesn't discriminate between vaxxers and anti-vaxxers, at least not until the vaccine is actually available, which would mean that the probability to receive a vaccination after infection is equal to the probability to receive a vaccination regardless of infection status. And then we could write down this probability as the size of V versus the size over the size of N, and deduct or get as the total population minus the vaccination minus the recovered population without the vaccinated people. In principle, this answer is justified, as survey studies suggest, because we do have a great collaboration with people from Erfurt University, and they were able to ask people, especially recovered people, how likely they were to get a vaccination. And actually, the number of people who had an intent to vaccinate themselves or to get vaccinated was of the same order as the number of people who actually got a vaccination later on in Germany. The problem is that we have very heterogeneous dynamics of infection and vaccination. So if you look at this, if there's a peak of infections first and then a peak of vaccinations afterwards, that is great, because then our assumption is justified. However, if there's a second peak afterwards and no vaccinations afterwards, then the assumption is not justified. And also, we don't yet consider it eligibility for vaccination or reinfection. Right, so what we did was to write down a very simple model where people just changed their states to infected, recovered, and we got that from data from officially data in the reporting system, and under ascertainment assumptions included eligibility for reinfection or vaccination, and then having official weekly data. So these are temporal rates here for vaccinations. And then, for example, for the age group 60 plus, we have these different dynamics here, and we can just feed those data into the model. And what comes out is that, for example, in the age group, which 60 plus, which is the most vulnerable age group for having severe disease of COVID-19, approximately 4.3% of this population is still immunologically naive. Having the spirit of keeping it simple in mind, we could also ignore the model that I just showed and just do the initial analysis, but split the whole thing into timeframes and then compute the size of recovered and the size of vaccinated and apply the formula. What we get is that if we take the this pre-period, then the number of infections plus vaccinations is about 21 million. And then post, the number of infections plus vaccinations is about 2.04 million. And taken together, this means that from this very back of the envelope calculation, we have a size of the population that's immunologically naive of 4.4%. So even though our initial model was relatively simple, we could have done simpler. Okay, some conclusive remarks. Many people in our field, myself included, we build our models and we make them more detailed and try to make them as realistic as possible. Not necessarily because that's our motivation. Also, it's just done because we want to convince medical professionals, which do like complexity, it seems. But what I learned from our research in the last 2 years is that simplicity is a virtue. And as this, I would like to conclude with a small example of modeling. For example, if we have premise that sometimes we perceive humans as smiling, and we want to have a model to find out why and or from which data we can deduce that. And we could have a very complex model and see, okay, we see that this model makes us think they are smiling. We could also have a very simple model and have a very simple analysis with the simple model, just playing around with mouth curvature and see that only this kind of mouth curvature we perceive as smiling. So we would see that the more simple model is, yeah, much more straightforward and easier to analyze than a more complex model like this. And with that, I would like to conclude and await your questions.
Thank you very much, Benjamin, for this nice, interesting talk and introduction to disease modeling and pandemic development.